Hey everybody, today we're going to talk about one of my favorite parts of chemistry, which is the concept of the mole. Now, a lot of people hear that term, they automatically start to think about the mole on your face or the mole in the ground, and I totally understand that, but today we're going to be talking about the chemistry mole, which sounds scary, but it's really not. So just to kind of put things in perspective for you, remember on day one, we talked about how chemistry is submicroscopic. So we're talking about things that we can't even see with a microscope. So teeny, 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 tiny. So when I say we're talking about the mole, we're going to use that to talk about large quantities of atoms, molecules, particles, ions, whatever word you want to use, okay? Now, just to give you an idea here, okay, an atom is so tiny that you can fit millions of atoms onto your fingernail, okay? Millions of atoms onto your fingernail in the 1 centimeter space. So when we have to talk about how many atoms are present in a sample, right, the idea of quantifying that number without simplifying it is kind of scary, right? Talking about millions of things every time we say it. So, oh, how many atoms are in this sample? Oh, 26,352,336, right? That sounds scary. It sounds scarier than saying, oh, there is 1 mole of atoms present in that sample. So let's go ahead and talk a little bit more about the mole. So the mole, which again sounds scary, is not. Okay, the mole is a unit. Okay, and I'm going to attach a video to today's lesson down in the Google Classroom section, which is a really fun little tune if you're like into the cheesy tunes to help you remember things. But the mole, I'll put the mole, okay, is a unit to help chemists quantify large numbers, okay, of particles. Now, why do I use the term particles here? Well, remember in some of our early lessons, we talked a little bit about this term particles and how we use it for different things, okay? So if I'm talking about how many particles are present in a sample of an element, I might replace that word particle with the word atom, okay? So again, if we're talking about element samples, then I'm going to replace that word particle with the word atoms, okay? But if we're talking about something like a compound, we can't use the word atoms anymore because remember, when something's in the compound, they're chemically combined, and therefore we have to use the word molecules, okay? So when we're talking about compounds, we're going to use that term molecules. Okay, now what exactly then is a mole? How much is a mole? Okay, so a mole is 6.02 times 10 to the 23rd particles. Okay, and that's a lot. If you think about that, I don't even want to start writing that, right? That's 6 with 23 zeros that follow it, okay? That's a really big number of particles, okay? And this number, this 6.02 times 10 to the 23rd, is also known as Avogadro's number, okay? Avogadro's number. And he was a scientist that helped us determine that exact number of particles, okay? So that's the concept of the mole. Now let's use this concept to help us calculate some values. So if you're following along on my guided notes sheets, we are now below the definition of mole. If not, I'm going to go ahead and write out the problem for us here anyways. But what I want us to do is I want to know, okay, how many atoms, okay, are present in a 0.5 mole sample, okay, of copper. Okay, now again, taking a look at this question, right, we have one piece of information that's really important to us, and that's this 0.5 mole sample. The piece of information that we're missing is our conversion factor because, right, we're trying to go from moles to atoms. So we need to understand the conversion factor that's going to help us get from moles to atoms. So if we think back to what we just learned about, right, this Avogadro's number, this now becomes our conversion factor, okay? Because we have, for every 1 mole, 6.02 times 10 to the 23rd particles. Now again, in the problem, it depends on if we're talking about atoms, molecules, elements, compounds. So let's go back, okay? We have atoms because we're talking about a sample of copper. So therefore, our conversion factor that we're going to use is 1 mole is equal to 6.02 times 10 to the 23rd atoms. So let's go ahead and set this up using dimensional analysis. I have 0.5 moles, okay? And I want to know how many atoms are present. So we want moles to cancel. 1 mole goes on the bottom, and 6.02 times 10 to the 23rd atoms is up top. Now, again, the beauty of dimensional analysis, just by putting our units there and canceling our units, we now see that this is just a multiplication problem. So 0.5 times 6.02 times 10 to the 23rd, okay? So what do we get here? Okay, we end up getting 3.01 times 10 to the 23rd. Now, if this idea of using exponents in math really scares you, here's what I'd recommend. Complete 0.5 times 6.02 without the 10 to the 23rd, okay? If you get a number where the decimal place doesn't move, so for example, right, i.e. 0.5 times 6.02 gives us 3.01. The decimal place is still in the same place, then my exponent is still going to be times 10 to the 23rd. Okay, if my decimal place moves, that's where things start to get a little more tricky. Okay, and we'll try to look at an example like that in just a moment. Okay, so we get 3.01 times 10 to the 23rd atoms of copper. Okay, let's look at our next sample problem. Okay, so the next sample problem on our sheet asks, okay, how many molecules okay, are present in a 0.5 mole sample of water, okay? Now you might be looking at this and saying, we're using moles again. This time we're using molecules. Well, what's my conversion factor? Okay, well again, we only really have one conversion factor at this point, right? 1 mole is equal to 6.02 times 10 to the 23rd molecules, right? Or particles. And in this case, it's molecules because we're talking about a compound. Now, you are probably looking at me and saying, well, if that's the case, Miss Daly, then isn't this just the exact same answer? Let's set it up and find out. 0.5 moles, okay? 1 mole, 6.02 times 10 to the 23rd, okay, molecules. Okay, again, our units cancel, and it's already set up for us, which is amazing. So 0.5 times 6.02. So yeah, again, we get the exact same answer. We get 3.01 times 10 to the 23rd molecules. So you're probably saying, why did you make me just do this problem twice? What's the point in that, Miss Daly? And the point is that I wanted to show you that regardless of what we're talking about here, okay, the number is the same. The only thing that's changing is the word atoms or molecules, right? 1 mole, no matter what our substance is always 6.02 times 10 to the 23rd. So 1 mole, regardless of substance, okay, is always 6.02 times 10 to the 23rd. It is amazing that that's the case, okay? Now let's try one more problem because I did say that I would show you something where the number got a little bit bigger. So really quickly, and feel free to pause the video and try this on your own if you want to try it. But let's try, we have how many atoms, so the number of atoms in a 2-mole sample, okay, of iron. Okay? So in order to do this, again, we're going to set it up. Our conversion factor is 1 mole equals 6.02 times 10 to the 23rd, okay? And so we're going to set this up. We have 2 moles, okay, times 6.02 times 10 to the 23rd over 1 mole. Okay, moles cancel, and we're left here with our just multiplication problem, okay? And so here's what we do. 2 times 6.02 is going to give us 12.04. Now notice my decimal place moved to 1 bigger, okay? Because of that, anytime the decimal place moves, we're going to plus 1 on the exponent. Okay, and we're going to move that decimal place back and then add 1 to the exponent. So our answer here is going to be 1.204 times 10 to the 24th atoms. If you are big in using calculators, which is totally fine, you're more than welcome to use calculators. Make sure you're using parentheses in order to keep that exponent in the closed parentheses. All right, awesome. So let's go ahead and move forward. All right, so here's the thing, okay? The number of atoms present in a sample of water is equal to the number of atoms present in a sample of copper, so long as we have the same number of moles, right? So 0.5 moles, okay, of copper, okay, is 3.01 times 10 to the 24th particles, okay? 0.5 moles of water, okay, is the same thing, okay? 3.01 times 10 to the 24th particles. Now, I don't know if you've ever held a sample of copper versus a sample of water, and we might have 2 samples with equal numbers of particles, but there definitely is something different about those 2, okay? And what we realize is different about those 2 is the mass of those 2, okay? So they might have equal particles, but they do not have equal masses, okay? And so this gets us to the question of what is mass, okay? Or how do I determine the mass, okay? And that's the atomic mass. So the atomic mass of our sample, or just in general, what is the atomic mass? The atomic mass is literally defined as the mass of 1 mole of our substance. Okay, and we can find this mass on the periodic table. So if you have a periodic table handy, it's going to be that mass in the upper corner, okay? So for example, if you're checking out a periodic table, carbon is 12.01 grams for every 1 mole, grams per mole, okay? So let's go ahead and do one more practice problem. How many grams are present in a 2-mole sample of carbon? Okay, so again, how many grams are present in a 2-mole sample of carbon? Now, this is a different conversion factor. Our conversion factor is now 1 mole equals 12.01 grams. Okay, so 12.01 grams. So 2 moles, okay, 1 mole, 12.01 grams, and this is going to give us 24.02 grams. We're going to finish up the rest of the sheet at the beginning of class. See you tomorrow.